Hello guys, today we are going to discuss the new experiment. So Learner's Big Book has come up with an experiment of ORAC assay where the determination of antioxidants capacity will be done in foods. So here further the next slide in this it's the discussion, a small brief discussion where we are going to discuss regarding the what is ORAC. ORAC is nothing but the oxygen radical absorbance capacity by the antioxidants present in the foods. So here whichever the antioxidants present in the food, they are going to absorb or they are going to act on the free radicals present in our body. So whatever the food we are taking, it is having the antioxidant capacity or antioxidant action on the free radicals, which are the oxygen species, that is the reactive oxygen species or nitrogen oxygen species. So here we are going to study or know the capacity of those antioxidants present in the food. Now usually you have come across the tables like this on the internet or also in your books, library books or your own study books, where you will be having a ORAC value for each and every food, especially the fruits, nuts and many other foods. Here it will be equivalent to some standard antioxidant like vitamin C, E or the Trolox, this kind of the equivalent in micromoles. Here in this table you got artichoke hearts. On their weight of 100 grams, they are going to have 7904 ORAC value, where the ORAC value will be equivalent to the Trolox equivalent micromoles. So here this will be the antioxidant capacity of the artichoke. Now here further black bean is having this ORAC value, black blue this ORAC value, blackberry this one is the corresponding. Like this the following all foods are having their own ORAC values, where they are going to have these ORAC values at their 100 grams, which is equivalent to the Trolox equivalent micromole. So this is regarding the ORAC. You know that what is ORAC. Now here why it is very important. Here it is the part of the nutrition, where all the educated consumers are having the basic knowledge of this information of whatever the products they are consuming. So these products index is going to have the label with these ORAC values or the antioxidant information. So this potential of the ORAC is going to mention whatever the food the consumer is consuming is going to be how much beneficial. So this is regarding the ORAC. So in general, how the consumer or the citizen is having the knowledge. Majorly these information labels has or the index labels has been put on the major developed countries, and wherever the citizens are having this particular awareness of this particular nutrition based information related with the antioxidant or the ORAC value. Especially we will come across the composition with vitamin D, C, E and other antioxidants on many number of the food packets which we are buying in the markets in day-to-day life. So coming to the next slide, introduction is that that the antioxidants are present both as endogenous antioxidants and exogenous antioxidants. Now the endogenous antioxidants are present both in enzymatic and non-enzymatic forms. You know that how they are present. I don't want to elaborate those because these slides may go longer. Now here exogenous antioxidants can derive from natural sources like vitamins, flavonoids, anthocyanins, some mineral compounds, but can also be synthetic compounds like the butyl hydroxyniazole, butyl hydroxytoluene, galates, etc. Now when you are going to consider further, whatever till now we have discussed is regarding the antioxidants has been discovered. Now what we are discussing is that we also know that there are many more antioxidants present in the plants in the form of the foods, and also we can extract more antioxidants which are beneficial to our health. Now here these many thousands of unique antioxidant compounds present in plants, most of which has to be discovered yet. So we have not discovered those out of those many thousands. Now there is no experiment to measure all of antioxidants individually. Here individually in the sense we have vitamin C, vitamin E, vitamin D, vitamin K, like this. Those are known antioxidants and we have the procedures to measure them. So as we are speaking regarding the many thousands of unique antioxidants present, because of that for each and every unique antioxidant we cannot always make a single or separated form of the method to identify their potential. So instead of that we are going to use this ORAC method, which is going to measure the antioxidant activity of a food. So in the previous slide we have spoken that each food or whatever the fruit or walnut we have spoken there, it is going to have the ORAC potential. It is the oxygen radical and absorbance capacity, that is the antioxidant influence which can be made through those foods on our body, where they can counter out the free radicals present in the biological system. So here with the help of the ORAC method we can measure the antioxidant activity of a food rather than the levels of specific C and vitamin E, vitamin K, vitamin D. Like that we no need to measure the unique antioxidants. So instead we can measure the direct antioxidant activity of that food. So with the help of this ORAC method we will be able to get the antioxidant activity. ORAC captures the combined antioxidant effects of the various nutrients. Thus, nutrients are more effective in combination than they are individually. Now here, as we have spoken, and antioxidant effect, whatever the table which we have spoken in this slide here, this is the combined antioxidant or the effect which we have spoken. That is what called it as the combined antioxidant effects, which can be captured with the help of the ORAC. So thus nutrients are more effective in combination than they are individually. So the nutrients which we are consuming through the foods are more effective in combination than they are individually taken. So having natural kind of the fruits, nuts and other vegetables or fruits are going to be more beneficial than we are consuming the vitamins or nutrients or any other kind of the nutritions which are specifically separated and taken as the pills or the medicines. So in the next slide, this is the slide for ORAC, where ORAC is nothing but the oxygen radical absorption capacity assay is most popular method evaluating antioxidant potential of food products, which I have already spoken. ORAC method is based on the hydrogen atom transfer reaction between an antioxidant and free radical. Here in this figure you can see this will be the center one will be the free radical atom, where it is going to, or the molecule is going to influence the healthy atoms present in the biological system, where it is going to snatch an electron from the orbit and it is going to become neutral, but it is going to make this healthy atom which is present in the biological system to go, in the sense after the one electron has been snatched, this particular healthy atom is going to function abnormal. Because of that, the whatever the molecule is there, it is going to act abnormal and cause the side effects. If there are many free radicals, if the free radical influence is high within the biological system, it is going to make this kind of the snatches of electron from the biological system or the molecules present in the biological system, and it is going to cause the array of the effects. So because of that, there will be the what we call negative effect on the biological system, and this can be the cause for any medical attention or the signs or the symptoms. Now here, when you are going to add the antioxidant to the system or the biological system or into your experiment, what will happen? This antioxidant is readily going to share its electron with the free radical, but when it is going to share the electron with the free radical, the antioxidant remains neutral, and by sharing its electron with the free radical, it also makes the free radical neutral. So the antioxidants readily neutralizes the free radical. Because of this, what will happen? The free radical will not act on the biological system molecules, and they are not going to make those healthy atoms to the free radicals, and it is not going to cause any abnormality in the functioning of this particular atom, healthy atom. This is how the hydrogen atom transfers takes place. Now, ORAC method utilizes a radical initiator to generate peroxyl radical, which abstracts hydrogen atom from antioxidant, therefore inhibiting further reactions. Now here, as we have spoken, that the free radical which is going to act on the healthy atom, where it is going to cause the further reactions and it is going to be the further abnormality. But here, as we are speaking about this point, here this point is related with the method of the ORAC, where we are going to use the radical initiator like compound, chemical compound, which is called to be as the APH in short, where it is going to generate the peroxyl radical. Here, when you are going to consider peroxyl radical, this will be the peroxyl radical. Now here you can see two types of reactive species. One is reactive oxygen species, composed of oxygen here everywhere. Reactive nitrogen species are composed of nitrogen and oxygen. These are can also be said as RNOS in some titles while discussing the free radical. So here, when you are going to consider ROS, in ROS you will see peroxyl, where the molecule will be having the two oxygen atoms. Now here, when you are going to consider this peroxyl radical generated from the radical initiator is going to abstract hydrogen atom from antioxidant. Now abstract in the sense it is going to take or share or get donated from the antioxidant. The hydrogen atom is get donated from the antioxidant, and therefore this radical initiator is going to get neutralizes. Now further, it is going to inhibit the further reactions. Now in this small discussion, it is the complete and brief understanding of the ORAC. It is the experiment to quantify the total antioxidant capacity of a food by placing a sample of the food in a test tube along with certain molecules that generate free radical, which we have spoken in this point, and certain other molecules that are vulnerable to oxidation. Now here, certain other molecules which are vulnerable to oxidation in the sense, here as I have spoken that there will be healthy atoms, which has to have a role to where we can understand the free radicals. In the sense, in the same way, here the other molecules, we are going to consider a particular chemical here in the experiment which will be vulnerable to the oxidation. So that is going to react as the healthy atom reacts with the free radical, and it will be vulnerable to get deformed from its original form. So here further, when you are going to add antioxidant to this particular explanation, then there will be the action of the antioxidant on the radical activity. So this vulnerable to oxidation molecules like this healthy atoms are going to remain healthy or in their natural form. They are not going to deform. Now further in this slide we are going to discuss the APH, which we were discussing in last two slides. That is how it is going to work. So here, what is AAPH? AAPH is nothing but C8H20Cl2N6. It is also called AB, AP, AMPH, ABAPH, and it is the famous as a model of oxidant. So it is not an antioxidant, it's the oxidant. So it is going to cause the oxidation. So here APH is having a chemical names which is available in two forms here, like this: 2,2-azobis 2-amidinopropane dihydrochloride, 2,2-azobis 2-methylpropionamidine dihydrochloride. So further, the AAPH is the chemical compound used to study the chemistry of oxidation of drugs. Now, it is used as free radical generator, often in the study of lipid peroxidation and the characterization of antioxidants. So, for these two major research related, they are going to use this AAPH as the free radical generator. So here, the AAPH, when it is decomposed, it produces molecular nitrogen and two carbon radicals. The carbon radicals may combine to produce stable products or react with molecular oxygen to give peroxyl radical. Now here, this we can understand here. Here, this is the AAPH. So here further, when it is decomposed, it is going to give two nitrogen molecule where carbon central radical will be formed. Further, when it is going to escape from this solvent, and when it is reacted with oxygen, it is the peroxyl radical. Now further, when you are going to consider, in some cases it will be subjected to induced oxidation with different combination of binary mixtures like natural phenolics. So here also it is the similar kind of the reaction where the oxidation will be induced to make the APH as a free radical initiator. Now you can see the APH structure here. So this is regarding the APH, and next in this slide we discuss the Trolox. So here this will be the molecular formula, and this will be the UPSC name, that is 6-hydroxy 2,578 tetramethyl 2-carboxylic acid, and this will be the following the structural formula of Trolox. This will be the analog of the vitamin E, that is the substitute or the mirror image, or it is same as the feature of the vitamin E, that is the action as the antioxidant vitamin E. The Trolox is going to function as similar to that. That is what here. It is a water soluble analog of vitamin E and an antioxidant like vitamin E, and it is used in biological or biochemical applications to reduce oxidative stress or damage. Here it is mainly used in the biological experiment to suppress the oxidative stress and damage within the biological or biochemical applications. So Trolox is always used as a standard antioxidant for the antioxidant capacity assess. So here the Trolox and the vitamin C, these two are the major antioxidant or vitamins which are used as the standard reference antioxidants to measure the other antioxidants present within the samples. Now here in ORAC majorly I have seen the experiments which were discussing both the vitamin E, that is the Trolox, and vitamin C, which is the ascorbic acid, used as the standard reference to understand the amount of the antioxidant present in the samples which they are using to conduct the experiment. Now here further, Trolox equivalent antioxidant capacity is a measurement of antioxidant strength based on Trolox measured in units called Trolox equivalents. Now here, what is this Trolox equivalent? It is nothing but whatever the standard reference we are using, that is the vitamins, those we are going to take in the form of the known amounts like micromoles and other form of the molecular weights, where we are going to take those as the reference, where we are going to conduct those experiments where we are going to compare the sample antioxidant with that standard weights according to that particular calculations. There are many number of calculations which has been adopted on different research papers. Here, according to that calculation method, they are going to take the result of that antioxidant present in the sample and they are going to compare on the graphs of the Trolox standards, and there they are going to consider those values in those graph standards of the Trolox, and there they are going to call it to as that particular value of the calculation wherever it is going to get suited on the graph as the value which is equivalent to the Trolox. So that is what the Trolox equivalent, where we can consider it to be as the Trolox equivalent per gram or Trolox equivalent per ml. Further is the Fluorescein sodium salt. Here you can see it's C20H10O5Na2 and it is having the IUPAC name of disodium 2,3-oxidorothionyl benzoate. Now here you can see this will be the molecular structure, and fluorescein sodium salts are present in even different structures also, and also with the different IUPAC names, but the majorly used is the fluorescein sodium salt which we have shown here. Now here it's an organic compound and also a dye, because it is going to have the dark orange red powder slightly soluble in water and alcohol. Here it is widely used fluorescent tracer for many applications. Now here you know that it is very much intensified kind of the dye where this molecule is very used. So here intensified in the sense it is going to give a perfect absorbance when it is placed in the equipment to measure the absorbance. Now here when you are going to consider, fluorescein is photostable, that is why it is intense. Photostable in the sense when the sample has been taken after performing the experiment, that is whatever the reactions we are going to perform with the chemicals during the procedure, after that whatever the color has been developed, after the completion of the time of that experiment when we are going to measure under the equipment, that is the photospectrometer, there the light is going to pass through the, so during that time the whatever the photons, photovoltaic energy is going to pass through the sample, that is going to cause the reaction within the whatever the ionized form of the molecules are present. So when you are going to consider this fluorescein, when it has been added into the liquid, it is going to get into its ionized form. So during that time, whatever the light is going to strike the fluorescein, it is not going to make any difference to the fluorescein structure. So the intensity of that particular dye is going to remain the same. So it is the photostable, which is going to exhibit no significant change in fluorescence intensity over 35 minutes. So here, once the fluorescein has been used during the experiment, it is going to give a promising effect of it till 35 minutes to 40 minutes. So this has been the default time range which has been mentioned even in the research articles. Now here, peak excitation occurs at 494 nanometer and peak emission occurs at 521 nanometer. This is the standard one, that is the excitation and emission frequencies of 494 and 521 nanometers. So here again, the ionization equilibrium leads to specific pH dependent absorption and emission over the range of 5 to 9. Now, as I said, that once the fluorescein has been added into the liquid, it gets ionization, and when it subjected to its equilibrium, it is having a specific pH dependent absorption. Now that is between 5 to 9, and within this range of the pH you can measure or you can conduct any of the experiments where you will be going to get the results at its best. So that is what the explanation of this particular point. Further is, fluorescein has an isobaric point, equal absorption for all pH values at 460 nanometer. So here, when you are going to consider any pH where at this any pH, that is, it is not between only the 5 and 9. Yeah, majorly if you consider between 5 and 9, it will be good. More acidic or more basic pH doesn't give the good values. So here, when you are going to consider at any pH or all pHs, when you are going to consider 460 nanometer measurement, okay, of the sample, that is for the experiment, is going to be the isobaric point where it is going to use the specific wavelength number or frequency at which the total absorbance of the sample is not going to change during a chemical reaction or a physical change of the sample. Now, in this slide, we will discuss the principle. Before getting into the principle, we will have 3 lines of the discussion. That is, we have discussed AAPH, we have discussed the Trolox, and we have discussed the Fluorescein. So in this slide, we have discussed this particular brief phrases, that there will be the radical activity and certain other molecules that are vulnerable to oxidation. Here, radical activity will be of the AAPH, which we have discussed already. The vulnerable to oxidation, the molecules vulnerable to oxidation in this experiment is the fluorescein. So here you can see that radical mediated damage of fluorescein is going to take place. Here the ORAC will be measured of the AAPH because of the AAPH radical mediated damage of fluorescein, whereas this ORAC EPR, that is electron paramagnetic resonance based ORAC method, where there will be the electron paramagnetic, that is the snatching or the excited free radical is going to take the electron from the fluorescein. Okay, so here it is also called it as the resonance based ORAC method. So here directly measures the decrease of AAPH radical level by scavenging action of the antioxidant. As we add, because of the presence of the antioxidant, what will happen? Whatever the AAPH has been present in the medium will be scavenged or neutralized by the antioxidant substance. Because of that, what will happen? The fluorescein, which has not got into contact with the AAPH, is going to be saved. So this vulnerable molecule to oxidation is going to be safe because of the antioxidant, which is going to neutralize the radical where mediated by the AAPH. So here you can see reaction. This will be the AAPH, which will be decomposed to the free radical form, that is the carbon centered free radical form. Further, this carbon centered free radical form will be reacted with oxygen. So because of this, the peroxyl radical will be formed. This peroxyl radical is going to react with the fluorescent probe. So because of this, what will happen? Whatever the hydrogen atom is present, which will be snatched further by this peroxyl radical. Here you can see the fluorescein is going to get reduced, where hydrogen will be removed and passed to the peroxyl radical, and this peroxyl radical get neutralized from its free radical state, and the fluorescein is going to be reduced. Because of this, its reduction, it is going to lose its dye feature. So this is how this fluorescein molecule is vulnerable for this particular oxidation, where further it is going to be seen that this particular antioxidants are going to reduce the peroxyl radical, and they are going to save the fluorescein molecule. Now here we have mentioned the same in this slide. Free radical generates azo-initiator molecules of AAPH and produces peroxyl radical, and further this azo-initiators damages the fluorescence molecule. Adding antioxidant, on the other hand, are counteractive molecules to protect the fluorescent molecules from oxidative degeneration. Oxidative degeneration is by the AAPH radical initiators or azo-initiators, and further this saving of the fluorescence measure the fluorescent dye, which is the fluorescein. Then the degree of antioxidant activities protecting fluorescence was quantified. So hope I have spoken very clearly. And further is the required reagents. Here the required reagents are like the phosphate buffer and the blank and the Trolox, Fluorescein, AAPH and sample extraction. Now here you have to prepare the phosphate buffer as has been spoken here, where you are going to take 10.21 grams of monopotassium phosphate. So here remember, we are going to prepare phosphate buffer with the help of the two potassium phosphates. One is mono and other is the di. So with the help of these both mono diphosphate, potassium phosphate, we are going to prepare the phosphate buffer at pH 7.4. Here first we have to prepare potassium phosphate, that will be of 10.21 grams of monopotassium, will be dissolved in 700 ml of deionized water in a 1000 ml of volumetric flask, and further after dissolving it to complete, further we are going to make it the volume to 1000 ml. Further we are going to prepare potassium phosphate. Here 13.06 gram of dipotassium phosphate will be taken into 700 ml of deionized water, and further it will be dissolved very clearly and we are going to make it the volume to 1000 ml. Further, we are going to prepare the working buffer solution with the help of these both monopotassium phosphate and dipotassium phosphate solutions, which we have already spoken. Now here, whatever the mono and dipotassium phosphate solutions we have prepared are of 75 millimolar concentration. So this we have to note before preparing. So whatever the weights or the amount of this which we have taken and prepared are going to give the millimolar of 75. Further working buffer solution we are going to prepare like we are going to take a 100 ml beaker and we are going to add 800 ml of solution B. First we are going to add solution B. Further we are going to add solution A slowly to adjust the pH for 7.4. So here the first solution we are going to taking is the solution B, which should be of 800 ml, but whatever the solution A we are going adding, that is to make the pH 7.4, but not to take any particular amount to set the pH, but it is to be added to adjust the pH to 7.4. Remember this point. So this is how we are going to prepare the working buffer solution. Further is that these buffer solution should be having the pH of 7.4 and also the other solutions which we are preparing. Now here for blank we are going to use phosphate buffer which we are already prepared here, working buffer solution, to set the spectrophotometer to 0 reading. So that is the blank. Further is Trolox. Trolox has to be prepared of 2 millimolar concentration. So first we have to prepare the stock solution. Dissolve 0.074 grams in 100 ml of working phosphate buffer. So working phosphate buffer is this one. From here we are going to take the 100 ml of it and we are going to dissolve 0.074 grams of this Trolox, okay, where it is going to give the concentration of 2 millimolars. If you are going to dissolve 0.074 grams in 100 ml of working phosphate buffer, the concentration is going to get set to 2 millimolar. Now further from this we are going to take and prepare working standard solution of 6.25 micromoles, 12.5, 25, 50 and 100 micromoles from this 2 millimolar Trolox of standard, each of 1 ml. Now here we are going to prepare different standard references of micromoles. So from this 2 millimolars, this you have to make on your own because there are many online portals which helps you to calculate, and I believe you all are efficient in doing these calculations and taking the perfect concentrations while performing the experiment. Further is fluorescein. Fluorescein has to be of 10 millimolar concentration, where stock solution should be prepared by dissolving 0.033 grams in 10 ml of working buffer solution and store in dark amber bottle and to be pre-incubated in water at 37 degrees centigrade for at least 15 minutes before measurement for working solution. So you can prepare 10 millimolar frozen stock solution and you can keep it for any longer time, but when you are taking it out for the experiment to be performed, during that time it has to be incubated at 37 degrees centigrade. Further, this fluorescein working solution should be of 48 nanomolar. Here, whatever the stock solution is 10 micromolar, the working solution should be of 48 nanomolar. Remember, this is the difference. So here it has to be prepared by taking 12 nanoliter of stock solution to 2.25 ml with working buffer solution. So whatever the working buffer solution we are preparing here, that has to be taken of 2.25 ml, and to that we are going to add 12 nanoliter of stock solution of fluorescein. Further, the note has been given that it has to be prepared freshly every time when you are going to perform the experiments, because fluorescein, once it is going to get to the buffer, it is going to have its intense dye capacity only for 35 to 40 minutes. So here this is what the reason why we have to prepare freshly every time. Further is APH. So APH we can prepare directly as the working stock. No need to prepare stock solution here. So every time during the experiment you can prepare working stock directly. It has to be 153 millimolar concentration, where you have to dissolve 0.025 APH in phosphate buffer of 50 ml and kept on ice. So here, which is going to be the APH solution. So here further you are going to prepare the sample extraction. Here this test samples has to be of 1 gram of the sample, which has to be dissolved in 40 ml of or extracted in the 40 ml of acetone water mixture, which will be 50:50 volume by volume at room temperature on an orbital shaker for 1 hour. So followed by centrifugation at 4500 rpm for 15 minutes. Now whatever the sample you are taking of 1 gram, we have taken sample of 1 gram, we are not mentioning which sample it is. There are many samples, and related to that there are many ways of extraction of the sample is going to be there. So there are samples which are used like the blood, urine, fruits, or the food which you are consuming. Like this there are many where they are measuring the ORAC out of that also. So what we have taken is the plant sample itself, but we are not mentioning which plant and what part of the sample we have taken. But this particular extraction can be done to the any part of the plant, and you can extract the sample. And here it is with the help of the acetone water mixture, and the extraction will be with the orbital shaker for 1 hour and followed by centrifugation of 4500 rpm for 15 minutes. And further is the supernatant, which should be taken and diluted and has to be prepared further as the folds 5x, 6x, 7x, 8x and 10x. That is the 5 different folds will be prepared with the help of the phosphate buffer. Made each sample dilution of 1 ml. So whatever the 5x we are preparing, it has to be 1 ml, 6x 1 ml, 7x 1 ml, 8x 1 ml and 10x 1 ml. So here the dilution has to be done. And further is the procedure. Here the procedure is, we have made it this particular part to make sure that the people can understand very clearly. That you can see that there are around 11 cuvettes. Out of this, one will be the blank, other 5 will be the standard reference for Trolox, another 5 will be the sample which we are already spoken in the previous slide. That is 5 of standard Trolox from 0.625 to 100 micromoles, and here it is 5x to 10x folds. Now here we have created this particular site reference for the same, that what the blank is going to have as chemicals, what the standards and the samples are going to have the chemicals. So here you can see blank. So this we are going to discuss again when we are going to discuss the procedure and the protocol. Now here you understood that why we have mentioned this. So further, when you are going to consider here, this will be the protocol for this experiment. The protocol is what present in the procedure. So directly we are speaking or discussing the protocol itself. Here you can see that at the first we are going to add 2.25 ml of fluorescein working solution, which is of 48 nanomolar. Here this top point, 48 nanomolar, in each cuvette labeled of blank, standard and sample. So for to all the 11 cuvettes we are going to add 2.25 ml of fluorescein. Further we are going to add the standard Trolox in microliters. So here the standard Trolox we are going to take in the micromoles diluted of the Trolox stock solution. So that will be 6.25 micromolar will be of 375 microliters in first test tube. Further is 12.5, 25, 50 and 100, where all will be of 375 microliters corresponding to the concentrations here. Further, in the same way, the sample which has been extracted and taken and separated in the form of the concentration folds. Here we are also going to take 375 microliters from each respective with the concentration into the cuvettes. Now further, the blank is neither it is going to have the Trolox nor it is going to have the sample in it. It is only going to have the fluorescein and the buffer. Okay, in the sense whatever the buffer 375 microliters has been added and 2.425 ml of fluorescein has been added. Only these two chemicals compounds is going to be present in the blank. But and further, when you are going to consider here, after adding all the chemicals into their respective containers, here each mixture should be vigorously agitated. We are going to agitate or mix or shake those mixtures in proper way, so the reaction should happen in perfect manner, and it has to be incubated at room temperature for 30 seconds. And further, after 30 seconds, immediately after adding the chemicals, after 30 seconds, that is after agitating, we are going to take the fluorescence reading of this all containers. And further, when you are going to take that reading will consider to be as the F0. That is the first reading where the adding of the APH is not initiated. Here there is only the sample standard reference antioxidant, that is the Trolox and the fluorescein. So whatever the generated fluorescein is present here, which will be considered to be as the F0 absorbance, where that will be before to the reaction started. So there is no action of any free radical now. So that is the F0 frequency, intensity, absorbance reading. So further, here we are going to add 25 microliters of AAPH into each container as the F0 reading has been taken. So further, when you are going to add at the first AAPH, the 25 microliters. After adding the APH, you are going to agitate the containers in proper way, and you are going to wait for the reaction to take place between the antioxidant and the APH, and the fluorescein and the APH. So here this has to be given 5 minutes of time. So after 5 minutes you are going to take the fluorescent reading again. That will be F5. 5 is nothing but the 5 minutes after 5 minutes of adding the APH of 25 microliters. So here in the same manner, with the time control of 5 minutes, that is, now after 5 minutes of readings, again you are going to add the APH of 25 microliters. Here this again you are going to wait for more 5 minutes, so it will become 10 minutes in total. So it will be the next reading after the plus 5 minutes is F10. That is, you are going to take the second fluorescence intensity reading or absorbance reading, and that will be at F10. So here when you are going to consider, during this the samples should be incubated at 37 degrees centigrade to avoid reading errors. The maximum incubation degrees, that is 37 degrees. So at this 37 degrees, the action or the reaction of the APH with the antioxidant or the fluorescein will be at its good effect. So here they have asked to 37 degrees centigrade. In some articles they have asked at the room temperature itself. So this is because to avoid the errors in the experiment. So this will give the good results. So here like this you have to do the addition of the APH at each 5 minutes, like first during after F0, that is 25 microliters. After adding first addition at 5 minutes you are going to take the readings. After taking the readings again you are going to add 25 microliters of APH, and you are going to wait till plus 5 minutes isn't going to happen. That is at F10, that is the 10 minutes, you are going to be take again the reading, and you are going to add again the APH 25 microliters to all cuvettes. Like this you are going to repeat this particular part of the experiment till 35 or 40 or 45 minutes, that is with the 5 minutes of interval or time control. So each time you are going to measure the fluorescent intensity absorbance. So this is going to give the different absorbance values. The readings is going to be taken at the 493 nanometer excitation peak wavelength and 550 nanometer emission peak wavelength. So it will be under the fluorescence spectrophotometer. So those readings has to be tabulated like this. Now as I spoken, time control every 5 minutes, that is F0, F5, F10, F15, F20, F25, 30, 35, 40, 45. We have taken up to 45. So we have seen the fluorescence. So in some experiments and articles we have seen that they have shown like they have taken the readings, frequency readings, even at 30 seconds, 1 minute also. So they have given different graphs of those readings and also given the calculations in the enormous form. So given that type of the readings also can be taken. Now here what we have done is to make sure that the people can understand that these kind of readings, taking readings is very best compared to the whatever the microseconds or the small timings which has been mentioned in the many other articles, because here we will be very definite that the reaction has been taken place. So here, even instead of 5 minutes, you can also go for 3 minutes also, where you will get many number of slots to perform. That is, like here we got 9 slots from 5 minutes to 45. If you reduce to 3 minutes, then it will be more than 14 or 15 slots you are going to get. Now here you can see these are the absorbance values which we have taken or seen for Trolox, and this for the sample here. Now here the up one is the blank. Now further, when you are going to subject these values, here you can see we have subjected the values of Trolox. So this is how the line graph is going to be seen. It will be subjected to the time versus the relative fluorescence intensity. Time is 0, 5, 10, 15, 20, 25, 30, 35, 40 and up to 50 we have put. Now here, when you are going to consider whatever the values we have seen in the previous slide, it has been shown in the downfall of the intensity. Now here you can see series 1. This series 1 is the F0, that is the blank, and further is the 6.25 of the Trolox, and further 12, further 25, further is 50, and further is the 100. Now here, with the increase in the antioxidant, there is the less decrease in the fluorescent activity, because the antioxidant has caused the APH to react on the fluorescence. Whereas in the first one, you can see there is the direct decline in the fluorescein because there is no antioxidant in this. So whatever the amount of the APH we have added, that has directly acted on the fluorescence present in the blank. So here you can see this will be the blank, and all these other 5 will be the Trolox. So here you can see at the F0, this will be the F0, and further F5, F10, F15, F20, 25, 30, 35, 45, like this. So here, whatever the F0 is present, it is showing the high peak as similar to the others, the fluorescence. When you are going to add the APH after F0, at the first addition itself, the APH has acted on the fluorescein. As the fluorescein is vulnerable to the oxidation, it has oxidated the fluorescein, and the fluorescein dye intensity has been reduced here. So that amount of the fluorescein has got reduced further. Here in the 6.25 of Trolox, the fluorescein activity is better when compared to the blank. In the same manner here, compared to the previous, here previous, here better to the previous, here better to the previous. So the decline in the fluorescein is going to be seen decreasing with the increase in the antioxidant concentration present in the standard reference. So this is the graph plotted for the Trolox. Further is sample. Here also you can see the sample is showing very good response of the antioxidant, where it is saving the fluorescence intensity at the large because huge amount of the antioxidant in it. As similar as we have spoken early in the previous Trolox graph, here also you can see that the high amount of the antioxidant has given the perfect fight with the APH to have the fluorescein intensity intact, whereas with the less amount of the antioxidant, it has been seen that not given any good fight. So here you can see 5x concentration dilution, 6x is lesser than the concentration of the 5x. Here the concentration reduces. If the dilution is 7-fold, concentration diluted further, 8x dilutes the further, and 10x dilutes the further. So compared to 5x, the concentration of the 10x is very low. So here there is the decrease in the activity of the antioxidant on the APH. So here this is regarding the graph. Further is the area under curve calculation. So this is the very important part of this particular experiment. So here you are going to do the calculation in the form of the area under the curve, where you are going to consider these graphs and you are going to take the calculation into consideration. So here the equations will be like this. Here UUC has to be calculated for each, here like this, for each blank, UUC of blank, UUC of 6.25, UUC of 12.5, UUC of 25 micromolar, Trolox, UUC of 50 micromolar. So like this for sample also 10x, 8x, 7x, 6x, 5x has to be calculated. So that has to be done with the help of the equation 1, where AUC 1 plus RFU 5 RF4 0 has to be done. Here RFU 5 is relative fluorescence value of time point 0, that is the RF4. Here RFU 5 is the RFU X, where at 5 minutes we have taken the fluorescence value, that has to be put at the numerator, and for the RFU 0, that is the F0 what we have taken. So this 1 will be the default in the sense, as we have taken RFU 5 divided by RFU 0, here at the 1 it should be RFU 0 divided by RFU 0. So as if you divide RFU 0 by RFU 0, the answer will be 1 itself. So here we are going to keep it as 1, the default, and further whatever the summation we're doing, the average RFU 10 and RFU 15, RFU 40, RFU 45, that is whatever the 5, 10, 15, 20, 25, 30, 35, 40, 45, all will be divided by RFU 0 value, that is the F0 value, and we are going to get that particular calculations with the help of the trapezoidal method. Directly you cannot do this particular equation calculation. Here this we have done very differently. Calculating the AUC with the help of trapezoidal method is very good, because it has given the lot of hopes in the calculation and we got whatever the values. Now here when you are going to consider, here you can see F0, F5, F10, F15, F20, F24, F30, F40. This will be the first will be done for Trolox 6.5 micromoles, and further trapezoidal has been done for 12.5, and further trapezoidal method has been done for 25 micromolar, that is the AUC calculation of by trapezoidal method is done for 25, further 50 and further 100. Here you can see that. Now whatever the values we have got, here you can see 4.67, 5.11, 11, 5.67, 5.54, 5.96. So trapezoidal method is very easy and very understandable, very convenient way to calculate, and also it will be very easy to learn and teach to the students. So there are many other methods also that is not going to be very convenient for the students to calculate the UUC, because it is going to be very confusing. So here we have considered trapezoidal method especially for the student community to learn the UUC, how to calculate the UUC. Here, further we have done the trapezoidal method calculation UUC for sample, and also both for sample and the Trolox. In the same way we have calculated the UUC of blank also. Here we have taken it to as separately, because we were not able to add in these slides, because already they are very much congested with their 5 concentrations. See here this will be the time, this will be the x-axis, which are going to remain the default for all the concentrations. Now y-axis is going to differ because y-axis values are going to have the inflorescence frequency values here that are going to be present here. So these are going to be respective to the concentrations. So here in the pink you can see you are going to be 12.5, here it is going to be for 25, here it is going to be for 50, here it is going to be for 100. So these two are going to be default, and the other here from here to here, the three, this three and this three, this three and this three is going to be the separate concentration AUC calculations. Now here the AUC what we have gone for 6.5 micromolar is 4.67, here it is 12.5, here it is 5.67, here it is 5.54, here it is 5.56. This is the Trolox. Next is the sample. You can see here also the same. You can learn the trapezoidal method of calculation from your statistic lecturer or biostatistic professor or teacher. It is very easy to understand and calculate. Now here this is how the AUC has been calculated even in the research articles. If you have any particular question related with the AUC, you can ask me. Definitely I may share a link, video link, which will be helpful for you to understand how I have calculated the AUC. Even I will try to put the link in my description. Now here further these values will be noted, and after calculating AUC of the blank, further you are going to calculate the net AUC. So here this whole slide will be labeled as net AUC, as we need the AUC of blank. Here in the net AUC calculation we have taken this calculation consideration here. Now further, before going to the net AUC calculation, in the net AUC calculation we are going to use equation 2 will be like net AUC is equal to AUC of antioxidant minus AUC of blank. Here you can see net AUC of Trolox, net AUC of sample. So net AUC of Trolox will be AUC of Trolox antioxidant, which we have taken from the previous, where AUC of blank, which we have taken here, will be calculated, where Trolox concentration will be 6.2512, that will be taken considered here, and further Trolox AUC will be taken and blank AUC also be taken here. So Trolox AUC according to the concentration, corresponding to the concentration will be considered, and further we are going to consider this AUC and you are going to minus the blank AUC, so you get 1.2. This AUC, blank AUC, so you get here this AUC and blank AUC, so you get here this one blank, this one, and when you are going to come to the blank, it will be blank minus of blank, that is 0. So further net AUC of sample is AUC sample of antioxidant minus AUC blank. Here these are the fold of dilutions, concentration dilutions, the blank and the AUCs. That is net AUC of sample, that is because of 4.49 minus of 3.47, 5.61 minus of 3.47, like this, and this will be the net AUC of samples corresponding to the concentrations. Now further we are going to take the average of these, average of the Trolox net AUC will be 1.92, average of net AUC of sample 2.31. So here you can see we are going to consider the average net AUC of sample. So all the net AUCs will be summed and divided by 5, because it is having 5 different concentrations divided by 5. Here also it will be divided by 5. So you get 1.92 for Trolox, 2.31 for sample. Previously what the net AUC is, we have calculated for corresponding to the concentrations and the fold of dilution. Those has been subjected in these graphs here. So this is how it is going to appear, and related to the concentration and the fold of dilution. Further, here we are doing the exact calculation to know the amount of the antioxidant present in the sample, which will be Trolox equivalent in micromoles. Now this is the graph which we have taken here. From here to here, net UC will be these here. You can see 1.1, 1.64, 2.22, 0.07, 2.49. So this will be the net UC for Trolox. Here also the values are going to be present from the net UC, but here we are going to consider this Trolox net UC graph, which I have done some more features to the graph to make it very easy to read the graph after the calculation, so you can understand better. So here in this there are three types of calculations which we have mentioned here, how you can differently calculate with the help of the different formulas, and it will be better to understand that whatever the experiment we have done is the correct one. So or the calculations which we have done as the AUC is also the correct one. So here you can see the sample average net AUC has been taken 2.31, and the Trolox average net AUC is taken 1.292 only for the reference, but the major part which we are going to consider is the sample, so 2.31. Now here, based on the Trolox antioxidant standard curve, this is the Trolox antioxidant standard curve or the line graph for net AUC. Okay, the equivalent Trolox concentration is 76 micromolar. In the sense, here whatever the net AUC is present, 2.31, 2 is going to fall here. Okay, 2 is going to fall here, and 3 is going to be the here, and 1, and it is going to be dragged till here, so it is going to fall till here. So to this vertical there will be the incident line from the y-axis 2.31, and it is going to fall on the x-axis at this particular line. So here this line is going to be having 76 micromole of the value. Here from 60 to 80 there will be the 5 divisions. Each division will be having the 4 micromolar of the concentration. So 60, 64, 68, 72 and 76 micromolar. Antioxidant concentration in the sample is 76 micromolars. Now when you are going to consider this 76 micromolars of the concentration will be for 365 microliters of the antioxidant of the sample. At the protocol you can see that we have taken 375 microliters of the sample itself. So when you are going to consider, we have to calculate it for 1 ml, and also we have to observe that each whatever the 10x, 8x, 7x, 6x, 5x samples, that those are the dilution folds which we have considered, each are going to have the different concentration of the sample. So before to calculating separately to 10x, 5x, 7x, we are going to consider one understanding here, that is when we have taken the average here, during this average, considering this average, we have collaborated even these folds of concentration into one. So whatever the value we have got, the net AUC is going to be the average for the overall sample concentrations. So when you are going to consider here the 375 microliters of the sample, which is going to have 76 micromoles of the antioxidant, is going to be average for all the concentrations, as the net AUC is the average for the samples. So when you are going to consider 76 micromole Trolox equivalent 365 microliter, 76 micromole Trolox equivalent per 365 microliters, that is 1 ml is equal to 1000 microliters. So 1 ml is equal to 2.66 folds of 375 microliters. So you have to multiply the 76 micromoles into 2.76. So when you are going to multiply, you are going to get the value of 2.216 micromole Trolox equivalent per ml of sample. So in the same way, it is also be corresponding to 202.16 micromole Trolox equivalent per gram of sample. 202.16 micromole Trolox equivalent ml of sample, and also it is going to correspond to 202.16 micromole Trolox equivalent per gram of sample. So this is how the calculation type 1 going to be. Next is calculation type 2. Here the same net AUC of Trolox graph. In this calculation type 2, the only thing which we have changed is that calculating the result with the help of the linear regression equation, that is y is equal to ax plus b. It is also called as the mx, some papers mx plus b. Like this it is going to differ, where further it will be derived to x is equal to y minus b of a, where x will be the identifying component, that is the sample antioxidant, that is Trolox equivalent micromole of the sample oxidant present in the sample, that has to be identified, and y minus b by a, where y will be the average net AUC 2.31 and b will be the intercept and a will be the slope. Now here when you are going to subject this Trolox values, net AUC values, in the linear regression line, I hope you know how to generate this. You will get the equation where it is going to have y is equal to 0.0109 x plus 1.4967. You can see ax plus b here. Y is equal to a value is this and x is present here, b value is this. Now when you are going to take this equation and subject the values, that is x will be Trolox equivalent micromole is equal to AUC minus intercept divided by slope. Trolox equivalents micromoles is equal to AUC minus b by a. So 2.31 from here, 1.4967 from here, that is b value, and to the whole divided by a, 0.0109 here. So it will be 74.61 micromole. So Trolox equivalent will be 74.61 micromole of antioxidant present in the sample. So as in the previous slide I have spoken that whatever the value we got is for the 375 microliters, which will be the net average AUC. So further it has to be multiplied to the 2.66 folds, that is 375 microliters will be present in the 2.66 folds for 1000 microliters. So 1000 microliters will be having 2.66 times of the 375 microliters. So 74.61 will be multiplied. So this will be the values of 198.46 micromoles of Trolox equivalent per ml of sample and per ml of gram. So this is how it will be. Further is calculation type 3. In this, net use of Trolox, the graph is the same, and net use of sample, as you can see this sample net use graph, which will be having the dilutions like 10x, 8x, 7x, 6x and 5x. Here first we will discuss the how calculation is. Here also you get the regression curve, that is the regression line has to be generated and equation has to be generated with that. Even on this net use sample you have to generate the regression line, but here I cannot do that because the values are going to have the alphanumeric. So because of this alphanumeric nature, we cannot generate the regression line and its equation. So if I had only the numeric concentrations, okay, then I would have been able to generated the linear regression line, and I would have got this equation even here. Now here, what is the calculation? How the calculation can be done? If we would have generated the linear regression equations on both the sides, and we have considered the slope values, where slope regression curve value will be taken. Slope regression curve of Trolox, that is at the numerator the sample, at the denominator the Trolox. So the slope regression value is 0.0109 here, that will be taken here in the bottom. If I had generated this equation here, would have taken this slope value, that is the a value from here, ax here, that is in this equation a value here, and I would have divided these both values, and I would have got the corresponding values as 74.61 and 76 micromoles. So out of these two, or near to these two, I would have got the values. So all these three types of calculations are very easy to do and perform the experiment. So this is the ORAC experiment which we have performed, and I hope I have spoken quite clearly, which is very much understandable to you. If you have any doubts and questions, you can raise those in the comments, and I will be very much glad to reply to you guys. If there are any mistakes and any corrections has to be done, and any wrong explanations has been done, or somewhere you cannot follow, please comment in the comment box so I can clear. So this is regarding the ORAC assay. I hope I was very clear. Thank you for your support, and please subscribe to my Learner's Big Book, and be visiting. We will be coming with different experiments. We have decided to give frequent uploads after correcting many of our mistakes in the experiments, and to give good slides to you guys. Thank you very much.